This is a fractal. It's called the Koch snowflake. Fractals are I don't know if I can define them, but one way you can define them is it's a very simple rule repeated over and over and over again. So here's my simple rule. I start with a triangle. It's an equilateral triangle. And my simple rule is remove the middle third of each side and draw a new triangle. So I'll try that. Remove the middle third and draw a new triangle. Remove the middle third, draw a new triangle. Remove the middle third, draw a new triangle. You hear me? I just did that. Remove the middle third and draw a new triangle from, maybe my directions could be a little better, but you see what I just did?
I want to say I didn't bring my ruler to school.
Remove the middle third and add a new triangle. Okay, now, well, remove the middle third and make a new triangle out of that, sort of. All right, that's the rule. Now, repeat that ad infinitum, or forever. So now that I've done it once, that's called one iteration of the rule. Do it again. Oh, you mean go to this side, remove the middle third and add a triangle, remove the middle third, add a triangle, remove the middle third, add a... You with me? This is the second iteration of this rule. You with me? That was just the second iteration. You ready? Do it again, please. You're supposed to do it forever. So I'm going to do it again, please. And you create this beautiful kind of snowflake, and the word is fractal. They invented the word fractal kind of in the 80s, maybe late 70s, 90s. They invented the word. And I think what we're going to get is we're going to get something, and you can prove that it has infinite perimeter. I think we're going to get an infinite perimeter. As you can tell, I keep adding these little, I think I could get an infinite perimeter, but a finite area. Which is sort of goes back to that old improper integral where we had an infinite area that came out to be finite. Remember? I don't know, it's related, sort of related to that maybe. In the end here, this is called a Koch snowflake, and it's a beautiful thing. You run, what you do is you're a computer programmer, you don't really do it by hand like this. But anyway, I think you can prove that you're creating an infinite perimeter, but it encloses a finite area. Here's another one. Here's another one. Make a triangle, upside down triangle, connecting the midpoints, make a triangle and color it in. Or maybe like remove it. This one's called the Sierpinski triangle, I think. Sierpinski triangle. Oops, sorry.
Is that S-I-E-R?
I think so. You gotta bear with me. Yeah, S-I-E-R. It's my estimation of the spelling. Connect the midpoints, make a triangle, and block it out or remove it. Kind of maybe remove it, like cut it out, or I'm coloring it in. Anyway, that was one iteration. Do it again. Well, when you do it again, you do it to this. Color them, remove those. It's like Swiss cheese. Maybe they call this the Swiss cheese triangle. I don't know. It's like you're punching holes out of this. Okay, do it. That was the second iteration. Do it again. You're supposed to do this forever. You see what I'm doing? You see? And I don't know. It's just kind of it's a geometric pattern. What am I doing? Am I removing all the areas? See, that would be the question. Maybe you can tell I'm sort of creating infinite series here. I can add up the area that's removed. Or maybe I could add up, maybe I should add up the area that I've removed. And maybe eventually I'll remove all the area, or maybe not. Maybe I leave some area. Infinitely, I don't know. I can't remember what the proof of this one is. There's one in your book, similar to this snowflake. There's one in your book called a sphere flake. It says you have a sphere of radius whatever, and it says to that sphere, attach 9 little new spheres. All right. Oh, of 1/3 the radius, or something like that. So then you attach these 9 spheres to it. There's a nice picture in your book. And then to each of those, attach 9 more little spheres of 1/3. So then they've got these little spheres attached to that. To each one of those, there's 9 more little, you follow me? I mean, it just gets crazy. And to each of those, 9 more little spheres. And I think, again, what you can prove here, what they're asking you to prove, and this is in your book, I think you prove that the surface area diverges, yes, the surface area diverges, meaning it's infinite.
Right.
The total surface area of this thing is infinite, but the volume that it encloses is finite. Or if you made a series for the surface area, it would diverge because it goes to infinity. If you made a series for the volume, it would converge because I think it's finite. But you have to kind of, to do the series, you have to, well, anyway. I mean, you have to do a little math. I mean, you have to, what is the, hang on, I'll help you a little bit. What is the surface area? I think the surface area of a sphere is 4 pi r squared. Okay, so what was the r of the original one? I didn't even read this to you too well. I'm saying you had an original sphere with a radius of 1.
Right.
Now, and to that sphere, we're about to attach little spheres of radius 1. To the large sphere, 9 spheres of radius 1/3 are attached. So their radius is 1/3 squared. But now, how many of those are there? 9 of those. To each of those, holy shit, to each of those,
Okay.
I'm going to attach 9 little spheres. So how many of those little spheres will I have? Okay, how many original spheres was there? 1? Okay, there's 1 of those. And then I just attached 9 little spheres of radius 1/3. Now, to each of those, I'm going to attach 9. So I think I'm going to do 81 little spheres now. And what's their radius? 1/3 of the previous radius. That would be 1/9, I think, squared. You guys following me? I mean, you can do this. This is not that hard to do, but you got to get organized. And what am I doing? I'm adding up all the surface areas of all these little spheres. You do a little cleaning up. Maybe you could probably see it. If you do a little algebra and cleanup work here, what is this series really? What is this series? What's that first term? 4 pi? What's the next term?
R.
Look at the next term, though. What is it when you clean it up? 4 pi. I'm not doing, I just looked at this 1/9 and this 9 and canceled them. It's 4 pi. What's the next term when you clean it up?
Oh, it's also 4 pi.
Yeah, good job. Guess what? So we're we're adding up the surface area of all these little spheres we keep adding to the original sphere. Anyway, what do you think this surface area is going to add up to? Infinity. I mean, I'm adding 4 pi infinite number of times, apparently. Okay, so that's kind of what we said 10 minutes ago. The surface area can be proven to be infinite. Now do the volume, and you might be able to prove it's finite somehow. I don't think I want to do that. I'm going to leave you hanging on that. You could do it yourself. I'll leave you hanging there. I want to move on here. I got class is almost over. These classes go by too fast. Don't you guys think they go by too fast? Oh, you don't have the same feeling I do? You're trying to get through a damn hour and 15 minutes. To me, it's over too fast. I'm moving on. Here's what I'm doing. I'm moving into 9.3. And there's 2 more tests to teach you about. This is back to talking about whether series converge or diverge. There's something called the integral test. That's going to be real fun. And then we have something called the p-series test. That's really cool. So these are in 9.3. There's more tests in 9.4 and 9.5 that I tend to skip. If we get to 9.6, there's something called the ratio test. There's also something else called the root test that I tend to skip that one too. So look at me. I'm building up a list of tests and I've skipped some. You hear me? And I'm doing that because I'm prioritizing my time and your time and the importance and relevancy to what we're doing. But these next 2 are kind of cool. The integral test says, let me see what this says. They have some conditions that have to be met. They say if f is positive, sometimes I gloss over some of these, and continuous, and decreasing, wow, for x greater than or equal to 1, and an equals f of n, then, here's the conclusion, the series an as n goes from 1 to infinity, and the improper integral from 1 to infinity of the function f of x both do the same thing. Either they both diverge or both converge. That's the integral test. And I'd rather not use it if I didn't have to. I don't want to, I mean, I love integrating. I'm sorry. No, I love integrating. I don't know. I like quicker tests. This test is kind of tough. This test says you got to meet these requirements. But then what it says is, notice this little funny part. Whatever the an is of the series, that we're calling that the function. So whatever is in the series is kind of a function of n. We write it over here as a function of x. And we worked on these improper integrals, thank you, in 8.8. And we worked on these, and so, remember, we know how to do these things, hopefully, in 8. And they either converge or diverge. We learned that was the first use of the word converge or diverge we ran into, was back here. If we do these integrals and we get a number, they converge. If we do these integrals and they get infinite, they diverge. But then we can take that knowledge and go back here and we can tell you that the series converges or diverges. See, in other words, this is a classic series. These are very famous classic series. Let's just talk about them. Let's pretend he showed up on a test, and I don't know what to do. Watch. Here's what you might do. You want to try a divergence test, you guys? Well, how do you do a divergence test? Take the limit as n goes to infinity. What do you get when you take the limit as n goes to infinity?
0.
You get 0. So what do you know? Nothing. That's the divergence test. If it's not 0, it diverges and you're done. But it is 0, so we don't know nothing. Thank you. You want to do a sequence of partial sums? Say no.
No.
Is it a geometric series?
No.
No. Okay, then maybe it's an integral test. Yeah? I mean, maybe. Let's just think about this. Are all the terms positive? Yes. Is it continuous? Yes. Is it decreasing? Yes. Then I'm allowed to do the integral test. I went over that fast, I'm sorry. And what that means is I should look at this integral from 1 to infinity of 1 over x dx. So see how you have the series 1 over n, and then you look at the integral 1 over x. And we looked at that integral, and we did him. First of all, he's called an improper integral. You make him proper by doing the limit as a goes to infinity, 1 to a of 1 over x dx. I guess I should go ahead and integrate. How do you integrate a 1 over x dx? ln of x from 1 to a. Plug in your a. You get the ln of a minus the ln of 1. Which is 0. So I just integrated and evaluated very quickly. I'm left with this. And don't forget, you're taking the limit as a goes to infinity. As a goes to infinity, you get the natural log of infinity. The natural log of infinity is infinity. It didn't take me too long, but it is a bit of work. I just did this integral and discovered he diverged. And therefore, by the integral test, I can say that the series diverges because they both do the same thing, is what the integral test says. If I find out he converges, then he converges. If I find out he diverges, then he diverges. They both do the same thing, the integral and the series. So I'm going to go back up here and say he diverges by the integral test. Even though maybe it's obvious I just did an integral test, I mean, this is how I want you to talk to me. You know, tell me what you did. What's your conclusion? What you did? There's your work. Did you guys remember? I don't know. Did you remember that he diverged? Maybe you didn't. Depends on how much homework you did in 8-8, I guess. In 8-8, you were supposed to investigate these dudes. Remember, how close were they to the x-axis and whether they converged or diverged. Anyway, he was the famous one that diverged, but anything with a higher, once I put it, he's got a power of x to the first. He diverges. But put a 2 there, or a 3 there, or a 4 there, and now he'll converge. And actually, you don't have to go to 2. Put a 1.5 or a 1.01, he'll converge if his power is bigger than 1. What am I trying to say? I'm trying to say, what if I wanted to do this problem now? Let's do this problem. 1 over n squared. Okay, that's a series. By the way, none of this stuff works up here. None of this works. Maybe I should do an integral test. I could do an integral test. If I do an integral test, that means I have to do this integral. I did this integral, and I just sort of told you what it would be. I mean, when I introduced these improper integrals, this is the first one I did. And then we got infinity and it diverged. And then this was the second one I did. You can go through the steps and see what happens, but I'll just tell you, it's a 1, and it converges. Remember? Do you remember? If you don't remember, go watch the video. I mean, when I introduced the improper integrals in 8.8, these are the 2 famous dudes. I introduced these, and why did I do them? Because I knew that I need them now. I mean, I need them here in 9.3. I'm studying these series. And how do you prove that this series diverges or converges? You do an integral test. I mean, it's totally related to this integral. And how do you prove whether this series diverges or converges? You do an integral test. So I skipped all the steps. You do this improper integral the proper way. He's not an ln. You know, when it's x squared, it's x to the -2. You add 1 to the power. It's not an ln, and so it converges. And it converges to 1. Now wait a minute.
Like this?
The integral has an area of 1, and we might say the integral converges to 1. But this series, hang on. So what does the integral test say? That when you do the integral and find out it converges, then the series converges. So did we find out this converges? Yes. So what about this? Converges by the integral test. But I do want to caution you, we do not know what it converges to. We do not know what it converges to, even though, Jesus. The reason we know it converges is because he converges. And the reason we know he converges is because we got an answer to the integral. And the answer to the integral is the area under the curve, but it's not what the series adds up to. So whatever number you get here that proves to you that this converges is not the sum of the series. But the fact that it's a number helps you prove that this converges. You with me? So we do not know. I'm going to call it. We know it converges, but we don't know what it converges to. It's because this guy converges. There's other weird problems that you might want to do an integral test for, but I'm going to get to the point here. I got 4 minutes of class left. And my point is this integral test leads right into what this famous P-series test. And so let's just check this out. And I just did 2. These are really P-series, you guys, is what I just did. I want to say, so a P-series test, or a P-series is, it's called a P-series. If it looks like this, n equals 1 to infinity, 1 over n to the p. It's a P-series if it looks like this. And guess what? These dudes converge when p is greater than 1. Is that what we just got done kind of saying? Mm-hmm. That is what we got done saying. And they diverge if p is less than or equal to 1. That power on that end that's in the denominator, they converge and diverge. So now I don't even have to do an integral test, or the guts behind a P-series test is the integral test. But now I wouldn't even do these with an integral test. I'd look at him and say, oh, p is 1. If p is 1, he diverges by the P-series test. I'd look at him and say, p is 2. If p is a 2, he converges by the P-series test.
How does it diverge if p equals 0, though? Because that would just be 1 over 1, and you can't put in infinity.
You're right. When p is less than 1, then you get to 0, or then you get to -1, and things might get a little weird. Although, maybe not. I don't think it, actually I think everything's still in place. You just asked me, what if p was 0? If p was 0, then this would be 1 over n to the 0. N to the 0 would be a 1, as n equals 1 to infinity. Now I'll tell you what, let's take a look at this series. Plug in a 1 and tell me what you get.
A 1.
Thank you, there's nowhere to plug in a 1. Okay, now plug in a 2 and tell me what you get.
A 1.
Plug in a 3 and tell me what you get.
A 1.
Okay, so guess what?
Okay, it's still negative.
So the terms themselves are 1s. But keep in mind you're in series, and if you're in series, you're adding up those terms, and if you're adding a 1 to a 1 to a 1 to a 1 forever, what will it add up to?
Infinity.
Infinity, therefore the series diverges. Right.
Okay. I'm cool with that.
Yeah, I know. Good. I don't know, what did I just do? I took 10, 15 minutes here and went through 9.3 real quick, you guys. A real quick version of 9.3. Integral test, which leads to P-series test. So catch up to me. I'll see you Friday. I might help you with some more homework. I might move on into 9.6. I might take a big leap Friday. We're probably, Wednesday. I'll see you Wednesday. We're probably taking a quiz soon, like Friday. And a test the following Friday. Maybe a take-home quiz coming soon.